Hello, a great welcome to this series on PLAXIS. Myself Jayarajan P. This is tutorial number 8 and it will demonstrate the geotechnical capacity calculation of a single poured pile in compression. So let me take you to the problem statement. So for this tutorial we consider a bored cast in situ concrete pile of diameter 600 mm and length 15 meters. The pile is constructed in a strata which consists of two soil layers, a clay layer which extends for 10 meters and the balance, that is 20 meters, consisting silty sand. The properties of both the clay and the silty sand strata are given here, and for both the soils we use the Moore-Coulomb material model for the analysis, and the pile will be modeled using linear elastic non-porous material. So let us start the PLAXIS. Okay, so as usual we'll start with the title, so we'll just write on pile capacity calculation in compression. Okay, so now our soil model is of dimension 30 by 30. So accordingly, we'll fix the contours as minus 15, plus 15, again minus 15, then plus 15. So that's okay for us. So let us start defining the stratigraphy as usual. We'll place a borehole at the center. So we have the two layers. So just to start adding the two layers. And we know that the first layer will start from a 0 to say 10 meter deep, so we'll keep it as a minus 10, and the next one strata is of a 20 meters deep, so obviously this should be minus of 30, minus of 30. So this means that we have defined the stratigraphy consisting of two layers, and now let us start defining the materials. We proceed for defining first the clay material. So press the materials. So we'll define a new material. And here okay, we'll just write down clay. We'll just start filling the various properties. Now we shall proceed for defining the parameters, wherein we'll define the value. Okay, now next one is the interfaces. Here we need to define what will be the interface factor, which provides a factor correlating the interface strength to the adjacent soil strength. So for this case, what we'll do is that we'll provide a manual way of providing the R inter value, and for the clay strata we'll provide it as a 0.80. So this means that the clay strata is defined. Now let us proceed for defining the next, that is our silty sand strata. So press the new. So in both cases we are using the Moore-Coulomb with a drained condition. Let us proceed for the parameters. E value we will keep it as 10,000. And the C value we'll use it as a 10 with a phi value of 36 and the associated psi as 6 degrees. Now let us say as usual proceed for the interface. We'll give a manual method of defining the R inter, and in this case we'll define it as 0.90. This means that we have completed the properties of both the strata. So we can straight away select this. So we'll adjust the top strata, we have got the clay that is defined, and at the bottom strata we have got the silty sand, so that's also defined. And let us keep the head at minus 30 so that the effect of water table can be neglected. So this is okay for us. This means that here we complete now, right now, the definition of the soil strata, definition of the soil layers, and also their properties. So this is the corresponding model. So this means we are now ready to proceed to the structures mode. And the structures mode, our main job will be to create the volume pipe. So we start with the polyline option here. So let me just zoom this. Okay, so it's my polyline. I will just select the center and we'll select the shape as the circular one. And the segments, what we do is that we define the radius. This is basically is a 600 mm diapile, which means that the radius should be 0.3, and the direction angle, let us keep it as a, for example, say 20 degrees, or maybe say 15 degrees. 15 degrees. Now the general again will just define this axis to the offset as a minus of 0.3. So this means that yes, the definition of the polycurve is complete. You can say that is already defined. So once the polycurve is defined, we can straight away go for the surface creation. So press the create surface button. Now we shall extrude this surface, to generate our volume pipe. So let us zoom a little bit. Okay, fine. So we have selected the surface. Go for the extrude. And so we know that the total length of the pile is say 10 plus 5, that's equal to 15. So we'll keep it as a minus 15. So this is apply. Okay, so you can say that yes, we have generated the volume pile. Once we have generated the volume pile, what we can do is that we can just delete this surface, the top surface. We can also delete that the polyline, delete this, and then just proceed for decomposing this volume into surfaces. So remember, we have generated the top surface, bottom surface, everything. Now we are ready to proceed for the so-called definition of the interfaces. So create a positive interface for the side surfaces. So that is already been defined. You can see that yes. So this is the positive interface. Now we need to define an interface at the bottom as well. So we can just rotate this a little bit so that we'll be able to see the bottom surface, and we can zoom this it is so that we are comfortable. So you can select this bottom surface, right, in a similar way, create that positive interface. So you can see that yes, the interface is also generated. This means that the definition of the interfaces is complete, and here we need to define only one thing, that is the surface load. Or so in this case, what we do is that rather than the surface load, we'll apply a prescribed displacement. That will be more better, because that will be able to provide us a clear-cut idea of what exactly is the load applied and the corresponding displacement. So we go straight away over here, and this is the, or what we can do is that we can just zoom this. The best option is that zoom this, and we can rotate it a little bit so that we can able to select the surfaces. So what we do is that we select this top surface. Okay, so just right click it, and you can apply the so-called create surface prescribed displacement. So we have created a surface displacement, as you can see. Yes, we have created say -1 meter, which will obviously edit during our staged construction mode. So once that is over, we are ready to go to the mesh. But before going to the mesh, it will be better that we define the pile property as well. So go to this again, define the new material. So we'll write as the pile, and we'll use a linear elastic material, and we'll select the non-porous option. The unit weight will be fixed, and the parameters will keep it as a 25E6 as usual, and this is my 0.2. So this means we have defined the properties of the concrete pile also. So having done that, we are now ready to proceed to the mesh mode. So let us proceed further the mesh generation. So we'll generate the mesh. So we'll choose for this tutorial element distribution as course. Please remember that for the real geotechnical problems, we need to perform the so-called mesh sensitivity analysis, which is used to study or investigate the effect of the mesh sizes on the final results. And only based on the mesh sensitivity analysis, we should select the so-called element distribution. So for this tutorial, this is okay because we want to make a faster computation. So this is okay for me. So as you can see that the mesh generation is in progress. Okay, so let us visualize the mesh. Okay, fine. So let me just zoom it so that you'll be able to see. See, you can see that yes, both the soil as well as the pile in and around. So this is the mesh sizing adopted for the soil immediately around the pile. As you can see that the sizes are very smaller in comparison to the mesh sizes away from the pile. So that should be okay for us. So let us just close it. And now let's proceed straight away to the stage construction. And as usual, we have got an initial phase over here. And the initial phase, our aim is to just to generate the stresses with the surface. And so we'll keep everything okay. We'll calculation type as usual will be selected as the K0 procedures. This is okay for us. Now we shall go for the second phase, and this phase will select as the pile construction. Just double click it. We'll have it as the pile construction, and we'll start it from the initial phase, and all these default parameters will be kept as it is. So what is important is that during this pile construction, we need to ensure that the volumes earlier occupied by the soil should be replaced by the corresponding pile element. So what we can do is probably we can go straight to this and go to the volume, and the volume will find that yes, we have uh, a soil. This we can just replace it by the clay we can replace it by the pile. That's okay. And then the second one also you can just replace it by the pile. So that must be good enough for us. So and remember, so this means that the earlier soil column is now replaced by the pile column. So we'll keep for example, you can say that here also correspondingly it is already updated. So yes, it is already selected as a pile material. And we will keep here because we have constructed the pile, we'll keep the interface also on. So that is all about what we say as the second phase. Now we are ready to move on to the third phase, which is very important, where we are going to apply a prescribed displacement to the constructed pile. So add a new phase in the phase 2. So as you can see that we have phase 2, which will be starting from the pile construction phase, and we'll reset the earlier displacement to 0. And here, in order to get a more larger number of steps, what I will do is I will keep for example here the maximum for example the maximum load fraction per step instead of 0.5. I would like to keep it as for example say 0.1. And other parameters I'll keep the same. So this is okay for me. Now what I will do is for this phase 2, ensure that our purpose is to impose the prescribed displacement to the pile top. So go over here, uh, activate the surface displacement, and in the surface displacement ensure that we apply the, so we won't apply a 50 mm downward load, so minus 0.05 meters, that's okay for us. So this means we have applied the prescribed displacement in phase 2. Now we are ready to proceed to the calculation. So we can just save this once again, and before the calculation, we would like to select one point, reference point for our creation of or the generation of the curves. So we can have search closest, because we are going to select the center point of the point 0, 0. So this is the closest point that we have. So just update it and then proceed for the calculation. So you can see that yes, the calculations are in progress. We will wait. Okay, so the calculations are complete. Let us start reviewing the results. As usual, we will inspect the distribution of the stresses corresponding to the initial phase. So we'll go for the stresses, and here I want to see the sigma set distribution. So you can see that yes, the calculated stress is 480 kN per meter square. This exactly matches with our 16 into 30, that is 480 kN per meter square. Now let us proceed for obtaining the deformation contours corresponding to the phase 2, which is very important for us. So we'll go for the deformations. So we want to see the total deformations that they used. So if you see the zoom this plan, you can see that this is how the deformation contours change in the plan. So in order to get a better view, let us take a cross section. So we'll take a cross section that is for example say from -20 to +20 +20. So that's okay. So you'll find that yes, this is how the deformation contours vary across the depth. So if you zoom this, you can notice one important thing, that is the deformation contours. Okay, so if I just rotate it a little bit, yes. So the deformation contours are very closer to the pile, and as they move away from this pile, you can find that yes, the value of the displacements decrease. And as the pile moves downward, you can see that the displacement contours are also maximum at the tip. So it is also possible for you to get how the displacement gradient. Okay, so let me just zoom this a little bit. Okay, how the displacement gradient or the contour occurs across the cross section. We can also draw a simple cross section across this. So something like this. I will not see the coordinate. Okay, so this is something like the displacement contour. You can see that yes, the displacement contour, it increases, and near the pile it suddenly increases, right? So we can also obtain the so-called the contour curve. Go to the tools, go to the cross section curve, and just select the phase 2. So this is okay. So you see this is what we call as the displacement or the settlement contour or the settlement gradient. As you can see that the settlement gradient is smaller away from the pile, but as it approaches near the pile, it suddenly increases. And here you will find that there's a gap. So this is actually, it increases up to the prescribed displacement of say 50 mm. So this is all about the displacement or the settlement contour across the cross section. Now let us go straight to obtain our curve. That is, let me just delete all these windows because I'm not interested in these windows. Okay, so means that this seems that I have deleted all the windows. I should have kept one. Okay, no issues. So let us go for now the generation of the curve, because we are interested in how the load versus the displacement curves looks like for the pile. So let me see the curve point. This is our curve point that is already selected. Go to the charts, go to the new. Okay, and what we want is that we want fz versus the four. So for example, here I want to select the point A. I want to select the deformations, total displacement, use it. Okay, fine. So this is how the curve looks like. So you can say that yes, starts from for example 0 0 curve. Okay, so this is how it looks like. Right, you can see that this is my use it increases from 0 to 0.05, and here we can see that the loads, you can also go over here, you can better do the, for example, the flip horizontal and the, okay, flip horizontal, and I also want to flip the vertical as well. So apply, okay. So here you can find that this is how the load displacement curve changes. So for example, as the load increases, we can say that almost at a load value of 1500 kilonewton, we find that the displacement, corresponding displacement is of the order of 50 mm. So this could be, considering the trend of the curve, this could be considered as an ultimate load. And now the computation of the safe load from the load versus the settlement curve basically depends upon the code which you have selected. It could be Indian code, it could be Euro code, it could be an American code. Accordingly, you have to read out the permissible safe load for the design from this curve. So that's all for this tutorial. But before leaving this, I would like to show you a copy. I have extracted all the data from this curve and I have pasted it into the Excel file. I want to show to you that also. So you can say that this is my curve, right? So we can see that it is the load settlement curve is almost linear up to 1250, and it goes to a purely nonlinear behavior starting from this point, and we can see that as discussed 1500 km could be considered as the ultimate load for this, which happens at a settlement of 50 mm. And please remember that the load settlement curve is purely depending upon the pile type. If it is a friction pile, it is a different, because to mobilize the total friction capacity, we require only a displacement of the order of say 5 to 10 mm. Whereas to mobilize the full tip capacity, you require a very large very large settlement, and this could be of the order of say 10% of the pile diameter. This is what the observations and the researchers tells us. So fine. So that's all for this tutorial. Thank you very much for viewing.